All right, so this lesson is on distance, displacement, and position. And what we're going to be able to do by the end of this lesson is differentiate between those three terms. Differentiate is just a fancy word for being able to tell the difference between those three quantities. And the way that we're going to do this is by identifying whether or not those quantities are scalar or vector quantities. And the reason that we're doing this is because we want to know when it's going to be easiest for us to work with position, when it's going to be easiest to work with distance, and when it'll be easiest to work with displacement. Every situation to a physicist is unique. Every problem is going to be unique. And these three different quantities have their merits in three different ways. So let's explore that. So motion can be described with two different types of quantities. Let's watch this quick video as an introduction to those quantities. Now when I click on it, it's supposed to take me to YouTube. Let's try this, hope that it works.
Hey. I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah! Check out my new weapon. Piranha gun! Oh yes! Fires live piranhas. Ever seen one before? No, you haven't. I invented it. Do you want a demonstration? Oh! Ah! Shoot! It's so difficult sometimes to get the piranha back inside.
So that was a funny little video about vectors. So a scalar quantity is different from a vector quantity because it only has magnitude. So the character Vector was harping that he has direction and magnitude. So scalars lack direction, meaning they're only a numerical value. So some examples of this might be if I was saying, hey, I was driving 60 miles per hour. That's a quantity that's got a magnitude, which is 60. But it doesn't give me a direction that I was going that amount of miles per hour in. Another example might be 21 inches. Maybe I measure that something is 21 inches in length. Maybe I measure that two objects are 21 inches away from each other. Either way, this quantity written as it is only has a magnitude of 21. It's got no directional value. So if these were on instructions, I don't know if I'm being instructed to measure 21 inches west, east, north, south, I'm not sure. And even quantities like time. Time, like 60 seconds. Again, is a quantity without direction. Now, how you could give time direction, I don't know. So I think time is always a scalar quantity because when I put my mind to it, I can't think of a scenario where I would have directional time. So there are some quantities that will always just be scalar quantities. That being said, like Vector was saying in his video when he was introducing himself, vectors are quantities with magnitude and direction. Since they have magnitude and direction, they can be represented with arrows. So for example, I could say that I was driving 60 miles per hour west or 50 miles per hour east. Oh wait, I said that backwards. East was the first one, west was the left one. I'm very tired. Anyway, I could say that this bookshelf, that's a really short bookshelf, maybe this book is 21 inches tall. I could say that this stair step is 21 inches down. Or I could give directions with a series of scalar quantities. For example, I could say, hey, you're going to head north for 3 miles and then west for 4 miles. Or I could do opposite directions, and say you're going to go west for 4 miles, and then south 3 miles. But all of these quantities have directions associated with them with the arrows. Now, if I didn't have arrows with them, I would just be using the verbal descriptors like what I was using as I was reading it out loud. For example, west. No, that's west, right? No, that's east again. I did it again. What is the matter with me? East, west, north, south. Now, another way that you could do it is using positive and negative values. So in math, going up is usually a positive direction, and going right on a graph is also a positive direction. It's considered positive because you're getting more positive x and y values. On a graph, going left would be the negative direction, and going down would be the negative direction. So sometimes we might do descriptors with north, east, south, west. Sometimes we might do descriptors with positive, negative, and other times we might just draw arrows to make our direction obvious if that's the easiest way to go about doing this. But in any case, a vector quantity is always going to have magnitude and direction. That's still purple. I meant to change colors. Oh, I did it again, blue. And let's make it larger. Magnitude and direction. Beautiful. Moving on to the next page. So I've got this humdinger of a question that I really want you to take your time with. Like really want you to take your time with. We've got the boy walking his dog and the girl walking home with her book bag. And they obviously took two very different paths. I want you to do this little thought experiment. Who traveled farther? Now really take your time, really ponder this, take in the picture for all that it's worth. If you want to pause the video and take out a ruler, that's fine. I really want you to give this a lot of thought because it's not an obvious answer. There's a bit of ambiguity to this question. So I'm just kind of talking right now to give you more time to consider your answer. Do you have it? Do you have it? Have you thought of your answer? Okay, I'm going to assume you've got your answer. So let's talk about two different ways to describe farther, right? That's the ambiguous word in this question. I could describe farther as the length of my path traveled, or I could describe farther as how displaced my object is or how much its position has changed. For example, the little boy who walked his dog obviously traveled a longer path. If I were to take this red line and straighten it out, it would obviously be a much longer line than the path of the girl. However, the girl's position changed more than the boy's position changed. He's not as far away from where he started as the girl is. So if I was describing farther with the length of my path traveled, I'd say the boy went farther. If I was describing farther as in how far away they got from their position, I would say the girl went farther. So this is the predicament that physicists found themselves in all the time when they were trying to describe motion. There's a bit of ambiguity about how far you travel. So they use these terms like distance and displacement to differentiate between that ambiguity. So when I'm interested in the length of path traveled, I'm going to describe that person's travel as their distance traveled. This quantity is a scalar quantity. It is non-directional. I'm not interested if they went north, east, south, west, if they did a loop-de-loop during their travel. It doesn't matter to me. I'm truly just measuring the magnitude of the length of their path, whereas my displacement is a vector quantity. I'm concerned with how far away this object got from its starting position, and direction does matter. Did they get 3 miles away east, 3 miles away west? Because 3 miles away east is a very different ending position than 3 miles away west is. So I need direction to give me an idea of where my final position is. So I'm going to add that down here.
One moment. You seem to be missing something.
Direction informs us
This represents
of where
discipline,
the final position is.
and this represents strength.
So I can't have displacement
You need both to reach the
without
arrow.
having direction.